Microelectromechanical systems is the technology of very small devices. It merges at the nanoscale into nano-electromechanical systems and nanotechnology. MEMS are also referred to as micromachines in Japan, or microsystems technology in Europe. MEMS are separate and distinct from the hypothetical vision of molecular nanotechnology or molecular electronics. MEMS are made up of components between 1 to 100 micrometers in size, and MEMS devices generally range in size from 20 micrometers to a millimeter. They usually consist of a central unit that processes data and several components that interact with the surroundings such as microsensors. At these size scales, the standard constructs of classical physics are not always useful. Because of the large surface area to volume ratio of MEMS, surface effects such as electrostatics and wetting dominate over volume effects such as inertia or thermal mass. The potential of very small machines was appreciated before the technology existed that could make them. MEMS became practical once they could be fabricated using modified semiconductor device fabrication technologies, normally used to make electronics. These include molding and plating, wet etching and dry etching, electro-discharge machining, and other technologies capable of manufacturing small devices. An early example of a MEMS device is the resistor, an electromechanical monolithic resonator. Materials for MEMS manufacturing. The fabrication of MEMS evolved from the process technology in semiconductor device fabrication, i.e., the basic techniques are deposition of material layers, patterning by photolithography and etching to produce the required shapes. Silicon is the material used to create most integrated circuits used in consumer electronics in the modern industry. The economies of scale, ready availability of cheap high-quality materials and ability to incorporate electronic functionality make silicon attractive for a wide variety of MEMS applications. Silicon also has significant advantages engendered through its material properties. In single crystal form, silicon is an almost perfect hooking material, meaning that when it is flexed there is virtually no hysteresis and hence almost no energy dissipation, as well as making for highly repeatable motion. This also makes silicon very reliable as it suffers very little fatigue and can have service lifetimes in the range of billions to trillions of cycles without breaking. Polymers. Even though the electronics industry provides an economy of scale for the silicon industry, crystalline silicon is still a complex and relatively expensive material to be produced. Polymers, on the other hand, can be produced in huge volumes, with a great variety of material characteristics. MEMS devices can be made from polymers by processes such as injection molding, embossing or stereolithography, and are especially well suited to microfluidic applications such as disposable blood testing cartridges. Metals can also be used to create MEMS elements. While metals do not have some of the advantages displayed by silicon in terms of mechanical properties, when used within their limitations, metals can exhibit very high degrees of reliability. Metals can be deposited by electroplating, evaporation, and sputtering processes. Commonly used metals include gold, nickel, aluminium, copper, chromium, titanium, tungsten, platinum, and silver. Ceramics. The nitrides of silicon, aluminium and titanium, as well as silicon carbide and other ceramics, are increasingly applied in MEMS fabrication due to advantageous combinations of material properties. ALN crystallizes in the wurtzite structure and thus shows pyroelectric and piezoelectric properties, enabling sensors, for instance, with sensitivity to normal and shear forces. Tin, on the other hand, exhibits a high electrical conductivity and large elastic modulus, allowing to realize electrostatic MEMS actuation schemes with ultra-thin membranes. Moreover, the high resistance of tin against biocorrosion qualifies the material for applications in biogenic environments and in biosensors. MEMS basic processes. Deposition processes. One of the basic building blocks in MEMS processing is the ability to deposit thin films of material with thickness anywhere between a few nanometers to about 100 micrometers. There are two types of deposition processes, as follows. Physical deposition. Physical vapor deposition consists of a process in which a material is removed from a target and deposited on a surface. Techniques to do this include the process of sputtering, in which an ion beam liberates atoms from a target, allowing them to move through the intervening space and deposit on the desired substrate, and evaporation, in which a material is evaporated from a target using either heat or an electron beam in a vacuum system. Chemical deposition. Chemical deposition techniques include chemical vapor deposition, in which a stream of source gas reacts on the substrate to grow the material desired. This can be further divided into categories depending on the details of the technique, for example, LPCVD and PECVD. Oxide films can also be grown by the technique of thermal oxidation, in which the wafer is exposed to oxygen and/or steam to grow a thin surface layer of silicon dioxide. Patterning. Patterning in MEMS is the transfer of a pattern into a material. Lithography. Lithography in MEMS context is typically the transfer of a pattern into a photosensitive material by selective exposure to a radiation source such as light. A photosensitive material is a material that experiences a change in its physical properties when exposed to a radiation source. If a photosensitive material is selectively exposed to radiation, the pattern of the radiation on the material is transferred to the material exposed. As the properties of the exposed and unexposed regions differs, this exposed region can then be removed or treated, providing a mask for the underlying substrate. Photolithography is typically used with metal or other thin film deposition, a wet and dry etching. Electron beam lithography. Electron beam lithography is the practice of scanning a beam of electrons in a patterned fashion across a surface covered with a film, and of selectively removing either exposed or non-exposed regions of the resist. The purpose, as with photolithography, is to create very small structures in the resist that can subsequently be transferred to the substrate material, often by etching. It was developed for manufacturing integrated circuits, and is also used for creating nanotechnology architectures. The primary advantage of electron beam lithography is that it is one of the ways to beat the diffraction limit of light and make features in the nanometer region. This form of maskless lithography has found wide usage in photomask making used in photolithography, low-volume production of semiconductor components, and research and development. The key limitation of electron beam lithography is throughput, i.e., the very long time it takes to expose an entire silicon wafer or glass substrate. A long exposure time leaves the user vulnerable to beam drift or instability which may occur during the exposure. Also, the turnaround time for reworking or redesign is lengthened unnecessarily if the pattern is not being changed the second time. Ion beam lithography. It is known that focused ion beam lithography has the capability of writing extremely fine lines without proximity effect. However, because the writing field in ion beam lithography is quite small, large area patterns must be created by stitching together the small fields. Ion track technology. Ion track technology is a deep cutting tool with a resolution limit around 8 nanometers applicable to radiation-resistant minerals, glasses and polymers. It is capable to generate holes in thin films without any development process. Structural depth can be defined either by ion range or by material thickness. Aspect ratios up to several 104 can be reached. The technique can shape and texture materials at a defined inclination angle. Random pattern. Single ion track structures. A named pattern consisting of individual single tracks can be generated. X-ray lithography. X-ray lithography is a process used in electronic industry to selectively remove parts of a thin film. It uses X-rays to transfer a geometric pattern from a mask to a light-sensitive chemical photoresist, or simply resist, on the substrate. A series of chemical treatments then engraves the produced pattern into the material underneath the photoresist. Diamond patterning. A simple way to carve or create patterns on the surface of nanodiamonds without damaging them could lead to a new photonic devices. Diamond patterning is a method of forming diamond MEMS. It is achieved by the lithographic application of diamond films to a substrate such as silicon. The patterns can be formed by selective deposition through a silicon dioxide mask, or by deposition followed by micromachining or focused ion beam milling. Etching processes. There are two basic categories of etching processes: wet etching and dry etching. In the former, the material is dissolved when immersed in a chemical solution. In the latter, the material is sputtered or dissolved using reactive ions or a vapor phase etchant. For a somewhat dated overview of MEMS etching technologies, wet etching. Wet chemical etching consists in selective removal of material by dipping a substrate into a solution that dissolves it. The chemical nature of this etching process provides a good selectivity, which means the etching rate of the target material is considerably higher than the mask material if selected carefully. Isotropic etching. Etching progresses at the same speed in all directions. Long and narrow holes in a mask will produce V-shaped grooves in the silicon. The surface of these grooves can be atomically smooth if the etch is carried out correctly, with dimensions and angles being extremely accurate. An isotropic etching. Some single crystal materials, such as silicon, will have different etching rates depending on the crystallographic orientation of the substrate. This is known as anisotropic etching, and one of the most common examples is the etching of silicon in Co, where C less than 111 greater than planes etch approximately 100 times slower than other planes. Therefore, etching a rectangular hole in a C wafer results in a pyramid-shaped etch pit with 54.7 degrees walls, instead of a hole with curved side walls as with isotropic etching. HF etching. Hydrofluoric acid is commonly used as an aqueous etchant for silicon dioxide, usually in 49% concentrated form, 5:1, 10:1 or 20:1 BO or BHF. They were first used in medieval times for glass etching. It was used in IC fabrication for patterning the gate oxide until the process step was replaced by RIE. Hydrofluoric acid is considered one of the more dangerous acids in the cleanroom. It penetrates the skin upon contact and it diffuses straight to the bone. Therefore, the damage is not felt until it is too late. Electrochemical etching. Electrochemical etching for dopant selective removal of silicon is a common method to automate and to selectively control etching. An active p-n diode junction is required, and either type of dopant can be the etch-resistant material. Boron is the most common etch-stop dopant. In combination with wet anisotropic etching as described above, ECE has been used successfully for controlling silicon diaphragm thickness in commercial piezo-resistive silicon pressure sensors. Selectively doped regions can be created either by implantation, diffusion, or epitaxial deposition of silicon. Dry etching. Vapor etching. Xenon difluoride. Xenon difluoride is a dry vapor phase isotropic etch for silicon originally applied for MEMS in 1995 at University of California, Los Angeles. Primarily used for releasing metal and dielectric structures by undercutting silicon. XEF2 has the advantage of a stiction-free release unlike wet etchants. Its etch selectivity to silicon is very high, allowing it to work with photoresist, CO2, silicon nitride, and various metals for masking. Its reaction to silicon is plasmoless, is purely chemical and spontaneous, and is often operated in pulse mode. Models of the etching action are available, and university laboratories and various commercial tools offer solutions using this approach. Plasma etching. Modern VLSI processes avoid wet etching, and use plasma etching instead. Plasma etchers can operate in several modes by adjusting the parameters of the plasma. Ordinary plasma etching operates between 0.1 and 5 torr. The plasma produces energetic free radicals, neutrally charged, that react at the surface of the wafer. Since neutral particles attack the wafer from all angles, this process is isotropic. Plasma etching can be isotropic, i.e., exhibiting a lateral undercut rate on a pattern surface approximately the same as its downward etch rate, or can be anisotropic, i.e., exhibiting a smaller lateral undercut rate than its downward etch rate. Such anisotropy is maximized in deep reactive ion etching. The use of the term anisotropy for plasma etching should not be conflated with the use of the same term when referring to orientation-dependent etching. The source gas for the plasma usually contains small molecules rich in chlorine or fluorine. For instance, carbon tetrachloride etches silicon and aluminium, and trifluoromethane etches silicon dioxide and silicon nitride. A plasma containing oxygen is used to oxidize photoresist and facilitate its removal. Ion milling, or sputter etching, uses lower pressures, often as low as 10⁻⁴ torr. It bombards the wafer with energetic ions of noble gases, often R+, which knock atoms from the substrate by transferring momentum. Because the etching is performed by ions, which approach the wafer approximately from one direction, this process is highly anisotropic. On the other hand, it tends to display poor selectivity. Reactive ion etching operates under conditions intermediate between sputter and plasma etching. Deep reactive ion etching modifies the RIE technique to produce deep, narrow features. Sputtering reactive ion etching. In reactive ion etching, the substrate is placed inside a reactor, and several gases are introduced. A plasma is struck in the gas mixture using an RF power source, which breaks the gas molecules into ions. The ions accelerate towards, and react with, the surface of the material being etched, forming another gaseous material. This is known as the chemical part of reactive ion etching. There is also a physical part, which is similar to the sputtering deposition process. If the ions have high enough energy, they can knock atoms out of the material to be etched without a chemical reaction. It is a very complex task to develop dry etch processes that balance chemical and physical etching, since there are many parameters to adjust. By changing the balance, it is possible to influence the anisotropy of the etching. Since the chemical part is isotropic and the physical part highly anisotropic, the combination can form sidewalls that have shapes from rounded to vertical. Deep RIE is a special subclass of RIE that is growing in popularity. In this process, etch depths of hundreds of micrometers are achieved with almost vertical sidewalls. The primary technology is based on the so-called Bosch process, named after the German company Robert Bosch, which filed the original patent, where two different gas compositions alternate in the reactor. Currently there are two variations of the DRIE. The first variation consists of 3 distinct steps, while the second variation only consists of 2 steps. In the first variation, the etch cycle is as follows. SF6 isotropic etch, C4F8 passivation, SF6 anisotropic etch for floor cleaning. In the second variation, steps are combined. Both variations operate similarly. The C4F8 creates a polymer on the surface of the substrate, and the second gas composition etches the substrate. The polymer is immediately sputtered away by the physical part of the etching, but only on the horizontal surfaces and not the sidewalls. Since the polymer only dissolves very slowly in the chemical part of the etching, it builds up on the sidewalls and protects them from etching. As a result, etching aspect ratios of 50:1 can be achieved. The process can easily be used to etch completely through a silicon substrate, and etch rates are 3 to 6 times higher than wet etching. Die preparation. After preparing a large number of MEMS devices on a silicon wafer, individual dies have to be separated, which is called die preparation in semiconductor technology. For some applications, the separation is preceded by wafer backgrinding in order to reduce the wafer thickness. Wafer dicing may then be performed either by sawing using a cooling liquid or a dry laser process called stealth dicing.